Yeah, hi folks, this is the next video for the Further Maths Year 1. We're starting a new chapter, chapter 8, working towards 8a, and it's proof by mathematical induction. Mathematical. Now, proof is a really interesting topic, and the reason it's interesting is because there's lots of different ways of proving statements. But this is all about a particular way made up of various steps. It's about proving statements. So, well, I want to prove that a statement is true for any value of n. Now, there's a little bit of notation to think about. N, this is our set notation, is an element of, and we can either have a big Z, that means positive integers, or, and these mean the same thing, n is an element of the set of natural numbers. So this big Greek n thing is defined as the set of natural numbers. And we want to prove statements for all positive values of n. So integer values of 1 or more. And we'll go through the different steps. But dogs are going for it. We'll go through the different steps for each example and explain them as we go. What I want to do is prove by mathematical induction that for all positive integers this summation is true. And the way mathematical induction works is it says if n is true for a number, then it's also true for the next number on. A bit like some people talk about building a wall. If I've got one layer of bricks, then I can build the next one, and therefore I can build the next one, and therefore I can build the next one. So if I can build one layer of bricks, I can build an infinitely high wall. So if I can prove that, I need to prove two things. I need to prove that if n is true for one number, then it's true for the next one. And I also need to prove that it's true for 1, because that then means it's true for 2, and that then means it's true for 3, etc, etc, etc. So, the first step they call the basis step. You don't need to remember the names. What I do is I set n equal to 1, look at the left hand side of my statement, r equals 1 to 1 to r minus 1, well that equals 2 times 1 minus 1, which is 1. Look at the right hand side of my statement, 1 squared is 1, and since the left hand side has the same value as the right hand side, that means my statement is true for n equals 1. So that's my first step, straightforward enough. Set n equal to 1, prove that left hand side equals right hand side. Step 2 is the assumption step. So step 2, we assume it's true for a general number k. And if that's true, because we're assuming that's true, it means we can say that my statement is true for 1 to k. Step 3 is where all your work is, and we're saying if it's true for this, then I'm going to show that it's true for k plus 1. So, so I write out the statement, the left hand side for k plus 1, and using what we've already talked about in the summations chapter, I know that that's actually equal to the statement for the summation for 1 to k plus the final term where I sub in k plus 1. Now what I want to show that this is true, but instead of k, I want to show that it's k plus 1. And at this point, I always find it useful to think about what am I actually trying to work towards here. I've got this on the left-hand side. I want k plus 1 squared on the right-hand side. So I always do is a little bit of side working out. I'm just going to replace this with k plus 1. We want k plus 1 squared, which of course I don't need to simplify any more than that, but I want to make this look like that. Okay, well, I already know, because I'm assuming that this is true, I already know that this is k squared. And of course, if I expand this out, k squared, I get k squared plus 2k plus 1. Well, that is equal to my initial statement, but with k instead of k plus 1 squared. Now this is a simple case to show you the process, but what I've done is I've said, if it's true for n equals k, then it's also true for n equals k plus 1. So if it's true for some number, then it's also true for the next number. And since we know one number for which it is true, we know that when n is 1 it's true, it must be true for n is 2. If it's true for n is 2, it must be true for n equals 3. If it's true for n equals 3, it must be true for n equals 4, and so on and so on and so on. Now you get marks from writing your conclusion out. And your conclusion, step 4, says, if true for n equals k, then it's true for n equals k plus 1. That's what we did in step 3. Since it's true for n equals 1, we showed that was the first thing we did. Since it's true for n equals 1, then by mathematical induction, it's true for any of the natural numbers, and I could either write that or write positive integers. They're both the same statement. You don't need both of these, but there's a mark for your conclusion. So the steps are: show that this is true when n equals 1. Assume it's true for n equals k, and show that if it's true for n equals k, then it's true for n equals k plus 1. And since we've got a case where it is true, then it must be true for n equals 2, n equals 3, n equals 4, etc, etc, etc. And you might want to go back and have a think about the logic behind this. I'm going to do example 2. So all of the first exercise are looking at summations. Okay, example 2. Prove by mathematical induction for positive integers n that this summation is true. This is the summations that we're given, the standard results that we're given in the formula booklet. So it's nice that we can at least see that this is a real thing rather than just be told it. Okay, if I set n equal to 1, the left hand side r equals 1 to n of r squared, well that equals 1. The right hand side, a sixth of 1 plus 1 times 2 plus 1 is a sixth of 6, which is 1. Since the left hand side equals the right hand side, this implies that true for n equals 1. That's my first step, my base step. Then I'm going to assume true for n equals k, which enables me to write out my statement with k instead of n. So here it is, r equals 1 to k of r squared equals blah blah blah. Remember what we want. We want to aim towards. We want that statement with k plus 1 instead of k. So let's write that out. K plus 1 over 6. K plus 1 plus 1. 2k plus 1 plus 1. Let's simplify that a little bit so we can see what we're going towards. K plus 2. 2k plus 2 plus 1 is 2k plus 3. Remember, the last thing we want to write in the next step is this statement here with k plus 1 instead of k. But I've simplified it a little bit because I know how to get to this through factorisation, because it's the same as the work we did in the summation chapter. Okay, so I've assumed true for n equals k. Let's write it out for n equals k plus 1. Well, that's true for n equals k plus the k plus 1th term. So again, understand what I've done here, and the reason I've done this is because I've got an expression for this from my previous assumptive step. So I can write out this. And I'm going to just write this as double brackets because I think this is probably easy to factorise in the next step. Look what I want. I want k plus 1 over 6. Well, I can take out my k plus 1 over 6 here. So k plus 1 over 6. My first term leaves me with a k times 2k plus 1. And understand this next step. I've had to put the 6 in because I've taken a factor of a 6 out. So if I expand that, 2k squared plus k plus 6k plus 6. Well, 2k squared plus 7k plus 6 will factorise to what I want. So I'm good. So for my last step, I'm just going to show that I can write this as my initial statement, my initial assumption, with k plus 1 instead of k. So k plus 1 over 6, k plus 1 plus 1, 2k plus 1 plus 1. So if it's true for n equals k, then it is also true for n equals k plus 1. So we'll write that if true for n equals k, then true for n equals k plus 1. Since it's true for n equals 1, then by mathematical induction, true for n is any of the positive integers. Okay, same method again for example 3. Prove by mathematical induction for n is all positive integers that this statement is true, this summation, r times 2 to the r equals 2, 1 plus n minus 1, 2 to the n. So let's let n equal 1. Left hand side gives me r equals 1 to 1 of r2 to the r. Well, I just sub in 1. 1 times 2 to the 1 is 2. Right hand side I sub in 1 again. 2 times 1 plus 0 times 2 to the n. 2 to the 1. Well, that's 2 times 1 which is 2. Good. Left hand side equals right hand side implies that it's true for n equals 1. So we're going to assume true for n equals k. So I can write this out with k instead of n. R equals 1 to k of r times 2 to the r equals 2. 1 plus k minus 1 times 2 to the k. Again, at this point I'm going to write out what I want, what I'm aiming for, and it's this with k plus 1 instead of k. So a little bit of side working out. We want 2, 1 plus k plus 1 minus 1. I'll just replace my k with k plus 1. K plus 1 minus 1 multiplied by 2 to the k plus 1. Simplify that a bit. And I'll just expand those brackets so that I can easily see what I'm trying to head for. Okay, so if I can get to this, then I can rewrite my statement with k plus 1 instead of k. So r equals 1 to k plus 1 of r2 to the r. Well, that equals r equals 1 to k of r2 to the r plus this with k plus 1 as r. So the sum of 1 to k plus the k plus 1th term. Well, I already have this from my previous statement, so it's 2 Yeah, now this is a really interesting one. What I'm going to do is I'm going to expand this bracket, so 2 plus, and I'm going to write, well, I won't write it yet. Okay. Now 2 times by 2 to the k, well, 2 times by 2 to the k, that's just 2 to the 1 times by 2 to the k, and of course I have my powers, so that's 2 to the k plus 1. So I can get my 2 to the k plus 1 term here. So 2 add 2 times 2 to the k, 2 times 2 times 2 to the k times by k minus 1 plus k plus 1 times 2 to the k plus 1, 2 plus k minus 1, 2 to the k plus 1, plus k plus 1, 2 to the k plus 1. I think this sort of exercise is where it's good to have a video, because you can pause, you can watch again, you can get your head around each line in your own time, sorry. Okay, I'm taking out 2 to the k plus 1 as a factor, because that's what I want here. So that's going to leave me k minus 1, add k plus 1, good, 2 plus 2k times by 2 to the k plus 1, which is where I want to be. So let's write it how I want it, with the k replaced by k plus 1. K plus 1 minus 1 times by 2 to the k plus 1. So all I've actually done is take a 2 out, 1 plus, and I've written k as k plus 1 minus 1 because I want to show that it's this k plus 1. Okay, good. So if it's true for n equals k, I've shown that it's true for n equals k plus 1. If true for n equals k, then true for n equals k plus 1. Since it's true for n equals 1, then by mathematical induction, true for n being any positive integer. I think, yep, that's your lot. So have a go at 8a. Let me know if you need anything. See you next time.